Hello everyone, my name is Michael Poor and I'm the Group 3 reporter for the jet engine experiment. An overview of our jet engine experiment. Our purpose is to gain an understanding of the Turbogen TM gas turbine electrical generation system. We'll do this by analyzing the data provided to us. Here we have a picture of our system as a whole, and we'll go through some of the main components of it. We have a centrifugal compressor to create thrust and drive the power turbine. This takes our fuel source and our air and it spins it really fast, and it causes an increase in pressure. This thrust is directed through the thrust transition deflector. Now some jet engines don't have this, and this would be normally where the thrust would be the propelling force. However, this turbine uses a transition deflector which drives a free turbine, which is an extra turbine. This free turbine drives an electrical alternator which generates electricity, and this is what makes our system unique. Our fuel is kerosene. This has an energy content of 135,000 BTU per gallon, which is roughly 37.6 megajoules per kilogram. It also has a density of 820.1 kilograms per meter cubed. This is the fuel that's very close to fuel that's used in most jet engines. We found a barometric pressure of 30.16 inches mercury. This experiment was done and recorded on March 28th, 2019 at 2:24 p.m. So we were able to go look at some archives of our weather and find this data. It should be noted that our data given to us from the experiment was reported in gauge pressure, but a lot of channels use atmospheric pressure, or a lot of different tables use atmospheric pressure. So we need to know what we're dealing with in case we want to look at different properties. Barometric pressure can be used and measured by barometers, but however, like I mentioned, for the purpose of the experiment, we were able to just go look at old weather channels. So this experiment involves a lot of looking at graph and data and see what happened over time. We picked up one point in our experiment at a peak value for our generator RPM. I picked 116 seconds, and so this will be the point we're looking at for most of our properties. Our compressor inlet pressure followed this trend line, as most of our values do, and it increased over time. We started out at a little, probably like 0.15 psig, and this increased to 0.6 psig. Over time, we can see that the outlet pressure did the same thing. However, our outlet pressure is much greater than our inlet pressure, which is expected of a compressor. This came out to a value of 21.6 psig. Our compressor temperatures were pretty constant throughout our inlet. Actually, they fluctuated a little bit. Of a value of 24.7 degrees Celsius was picked, but our outlet temperature was much higher, which was again expected, and this came out to 121.5 degrees Celsius. So for turbine 1, both our pressure and temperature between the inlet and the outlet, so from the inlet to the outlet, it will decrease. This is because pressure and temperature are being sacrificed in the turbine. So we start off with a value of 21.78 psig and end with a value of 3.1 psig. With our temperatures, we start with a value of 747.3 degrees Celsius and 571.5 degrees Celsius. And we can still see this increase in temperature over time. However, there is a decrease between the inlet and the outlet. Turbine 2, both the pressure and temperature use the same properties as the outlet of turbine 1. So the inlet uses the same properties as the outlet. So we have a pressure in the inlet of 3.1 psig and an outlet of 0.6 psig. Here we see the decrease in pressure again. Same thing with the temperature. We have a value starting with 571.5 degrees Celsius and ending with a value of 407.9 degrees Celsius. And this is again because our temperature and pressure are being sacrificed. So we can look at our fuel flow. Our fuel flow started at 10 liters per hour and ended with 23.371 liters per hour at a peak value. We can see that it was increased over time as we were spinning the generator faster, the engine faster, and everything. This explains a lot about our properties and why they followed this trend line. So going to our engine RPM, we have a peak value of 70,248.5 RPM. And this is at the beginning of the whole jet engine, and what is causing the compressor to spin really fast. Our generator RPM came out to be 1,468.6 RPM, and we can see a large spike compared to our rest of our data in the change between, let's say, point at time 100 seconds to our peak value. Our generator voltage came out to be 2.6 volts at our peak value, which started at roughly a little above 0 volts, as the generator required more voltage as it began to spin faster and faster. Same thing with our current. We got a peak value of 19.3 amps over time. Our power is dependent on both our voltage and current, so we know that how our power is supposed to behave. We came out the peak value of 87.7 watts over time, and we can see there's a massive spike in power as our generator RPM increases over time. And so this really concludes most of our data. Just thank you for listening.